still works. I don't know. I don't get it. It's Microsoft PowerPoint that's probably the biggest issue. Okay, these are videos we saw on Thursday. Yeah, of course, this is not going to play. Oh, maybe it will. Okay, we saw these videos on Thursday. This was the melt pool being formed from an X-ray point of view. The major thing to point out here is that for one of these, especially for the higher power laser, the cavity is driven in the base metal, and the high power laser trapped a pore within the structure. All right, and so those were some observations we did ahead on Thursday from X-ray images of what's going on inside the melt pool. Some other observations or things that you can pull from the literature and things I would say things we know, right, about powder bed fusion is that both layer height and part design matter, okay, in terms of what the thermal history is going to be. So some observations here. This is, to give you an idea of the orientation here, this would be X coming out of the page or screen, Y in this direction, this would be Z. So this is the way in which we build, right, in the Z direction. And we can do some really simple experiments to look and see how the way you design the process matters. Okay, so we'll talk about the modes of heat flow and where heat goes essentially. When you're heating metal, it has to go somewhere. The heat can't just stay resident in the part, it has to dissipate. But basically it's going to go from this top lasing surface down into the build plate is the main direction. And so you can do a really simple experiment. You can say, all right, let's build this part, just a random dummy part in this orientation, or flip it 180 degrees and build it in this orientation. And the main difference between these two here is that the thermal conductivity of this part, because this is wider at the bottom, is better in this part and this orientation than it is in this one, right? Because you have to pump a lot of heat to this skinny neck in this orientation. Right. So what that causes is it causes that this part is going to remain hotter than this part when you're building. And so you see that in the terms of this defect here. This defect is oxidation. So oxidation comes from having some amount of oxygen in your chamber. We can't completely evacuate oxygen from the chamber. It's somewhere less than 0.1%, but there is some amount of oxygen in the chamber. And oxidation happens when you have oxygen and basically a lot of materials, but especially metals, at elevated temperatures for long periods of time. Right? So you get things like this. You see this even to a smaller extent. In this example, you see a little bit of oxidation here, but again, the neck down here is wider here than it is in this one, so it's not as big of a deal. But you can do some really simple experiments to show that basically how you design your system, how you design your process matters, and that in general, as you go up, the part gets hotter, because that means you've had a longer period of time to be exposing the part to a laser energy, right? So it's going to get hotter. This is temperature measurements in the E-beam powder bed fusion. So same exact view as this right here, where this is kind of a top-down view. Instead of having a high-speed camera, you can have a thermal camera. So just like there's like night vision goggles that are kind of like thermal cameras, we can put these special forms of them that have higher temperature ranges into these types of systems and trying to understand what is the temperature of this part. So this may be a little tough to see, but the lower layers are down here in terms of the temperatures you experience. Oops. And the higher layers are up here. So this is layer 19 all the way up to layer 299. Okay, so as you continue to build this, the part or the background temperature is going to continue to get hotter, and this is very much dependent on design too. So you can see this is a poor design, and it got very, very hot. I forget what the design of this structure was. I think it was a simple block, so you didn't have this issue. Right? But that's another observation that we can make from just experiments people have run with powder bed fusion. Another one that's pretty similar is if you have overhangs in your part, you have essentially a hot spot. There is not an efficient way to exhaust heat when you have an overhang. So this is an experiment that this group intentionally did. And so what they imagine that this is the part at some part of the build, they intentionally put an overhang in the part. Right? So you have this little, say right here, you have this little island. All right? And then they have thermal cameras. So red is hotter, blue is colder here. And this is at the very first layer over the overhang, and this overhang would be right here. Okay, so when you're putting, in this case, E-beam energy, but you can say the exact same thing for laser energy, putting E-beam or laser energy into the part, and it's above a bunch of powder, the thermal conductivity of that, basically the thermal pathway is very inefficient above the powder. As soon as you get over top of the piece of metal, the heat can go down into the substrate very effectively. Right? So you can have essentially hot spots develop when you have overhangs, and that has, in general, is seen as a negative effect. Okay. So this is the very first layer over top of the overhangs. This is, you had an overhang, now you're starting to build material again. This is the third layer. You can see a small artifact of that right here. It's kind of this region. And then this is the 11th layer. And so by the 11th layer, then you have enough horizontal heat transfer that heat can be effectively exhausted. That's something to keep in mind in terms of trying to understand heat flow in these types of parts. Yes?
Is there any like rules of thumb for how thin a part should be if it is overhanging? Because I assume at some point there might be a hospital reporting overhang.
Yeah. Yeah, that's a long discussion. The next slide, no, not the next slide. Where do I have that? Let me find that. Oh, no, sorry, that was back. Not necessarily the thickness, but just the angle is often specified. So let's go back. Here we go. Right. So in the example, that group was intentionally creating a bad design. They're creating an overhang with an angle of 0 degrees. If this is the angle, how we measure the angle theta here. So in general, some people specify between 35 and 45 degrees. Anything greater than that is going to be just fine. Anything less than that is going to have some of these issues associated with it. In terms of how thin a part can be, that's something I don't know too much about. There are papers that kind of give general design guidelines for these types of things, and they talk about different. Oftentimes they talk about how thin a wall can be that's going straight up, not usually horizontal, because if you have a very thin wall, it's advantageous to build that thin wall in a straight up orientation. So what they did in this experiment is, in general, from a design point of view, is just a really bad idea. If you actually wanted to produce anything, you would never build a part like this. You'd actually rotate it 90 degrees in this direction to get that to build correctly. Yes?
We may have already discussed this, and so I apologize, but you mentioned E-beam kind of acute systems of the power around it. It's kind of like a semi-solid.
Yes.
Kind of caked together. Is there like no heat dissipation to the surrounding powder?
Yeah, we'll actually get into that a little bit. So there definitely is heat dissipation into the surrounding powder, and E-beam is going to be better because you get these little necks forming between the powders. And laser processes is going to be quite bad. So less than 1% in terms of conductivity of the unfused powder compared to fused metal. Okay. So we'll actually get into that from the literature in terms of what people have experimentally found in terms of the conductivities of powder versus the actual metal itself. Yeah, but think of this almost, and we'll get into how we'll specify this, but we'll consider this to be a Newman boundary condition in terms of no heat flow into that. As a simplification, it's not purely the case. You can imagine that some heat flows into the powder, but it's pretty small. Okay. All right, so yeah, so last thing, part stays hot in regions with poor thermal conductivity, like overhangs, other thin members. A lot of parts use these kind of like organic looking lattice or mesh tape structures, those are going to have pretty poor thermal conductivity, but you're also not putting all that much energy into those systems because you're not heating up the entire surface, you're just heating it in really small spots. So it's always a balance that goes on there. Okay. Other things that can be observed if you look at the literature is that temperature is higher at the corners of raster paths, and we'll talk about why this is the case too, but I think it probably makes sense. So it's tough to see. This is thermal camera images of these raster paths, and this is this actually isn't a thermal camera, this is just a single thermal diode, so a single element that's pointed at the melt pool, and this is right after a corner. You can see temperature spikes here, that's the hot temperature, and you can see artifacts of this in a few different ways. This is taking a laser in this direction, and then coming back and going this direction. Okay, and what you see here is you see that the melt pool width gets wider at this corner than it is in the center. All right, and that's precisely because basically the temperatures are higher. Temperature is higher at the corner of these raster paths. And I think you can probably understand why is you're heating up the part as it goes along, right? So basically the melt pool trail is hotter than when you started, and then you're running the laser then right adjacent to it on the way back. Okay, so you're hitting it pretty quick, in a pretty short period of time, you're hitting it twice with a laser. So you essentially preheated that region, then you heat it again, and so therefore it's going to have a higher temperature then. Okay, so then the melt pool expands. You can also see this in some of the videos we're looking at how the laser, especially when it's really high power, drives a hole into the material. So what you see in C is at the midpoint of B, so somewhere if you slice the sample here, you would see this nice weld pattern here, and then at the edge of this, right where the laser, basically the temperature is the highest, you can get these pore-like defects in the part, right, if you don't manage the temperatures properly. Right? And so this, you can see this from more of a macroscopic point of view. This is a seam between two different raster paths, so you had a raster path going here on this side, and raster path going here on this side, and this is where they intersect. And then you notice these little dimples all along the way. Okay. And so if you're trying to make a part with no porosity, that's a problem, right? So this is actually a pretty active research topic right now. A lot of labs are looking at this, and how do you can imagine how you can, from a controls point of view, if you know that this is going to happen, kind of invert that, right? So decrease the laser power when you're going into corners. No one's really doing that right now. They're just doing kind of experimental point of view, but is there potential research avenues, a way we can improve part of our future processes? Any questions on that? Yes?
So that's going to be a gradual change from like an upward curve to like a flat, and then there's a divot. Is there a transition between C and D? Because like as you, I don't know, frame the question.
Oh, okay. So you're saying there's no divot here, but at D there is a divot. Is this a gradual change?
Yeah. How does it change?
From my understanding, also looking at these, is this divot's actually fairly nonlinear. As you cross a certain point, and then this divot forms. All right, so here you see divots, and then just a little bit to the side of it, you don't see as much of a divot. So this would be kind of a pinhole type defect that would happen. Okay, so those are kind of observations. I'm going to spend the next few slides talking about what is understood thus far before we start to get into some analysis. Okay. All right, so what is understood from the literature, dozens to hundreds of people looking at this problem. What is understood is that in terms of physical process one, radiative energy is transferred to the powdered material. Laser absorption, and this, I'm saying laser, but this also could be, we make the same statement for E-beam. absorption is spatially distributed and lossy. So if we go back to the Rosenthal paper, we made an assumption, and that assumption was that all the laser energy is infinitesimally large for an infinitesimal width, right? We have a direct delta function that describes the laser. So that was a simplification to basically come up with some basic relationships. And you'll see again in a little bit that this is not necessarily true, that the laser has a finite width. And anyone who's played with a laser pointer has seen that, right? It's not this infinitesimally wide laser point. It has some sort of width associated with it. But to get into how the laser is actually putting energy on the surface, it's good to look at what is in the guts of these laser systems. So this is an example of a fiber-coupled laser. There are also other not fiber-coupled lasers that are used. But basically, you have laser coming in. You have some optics, being a single mirror or a bunch of mirrors, and then also beam expanders. And then somebody's going to cause it to come to a point. And then here is really what's doing a lot of the work is what's called a laser galvanometer. So what is a laser galvanometer? A galvanometer is essentially just a mirror in which you can change the position of that mirror. And usually when we talk about changing the positions of a mirror, we're talking about doing this really, really fast with a galvanometer. It's not like it's on a set screw or something where it's just manually done. It's motor controlled and it's done at a very, very high rate of speed. So for instance, we talked about some of the parameters before. These things move around in terms of the laser spot around 1.5 meters per second, right? But the bed is much, much less than 1.5 meters, right? So it's actually doing 1.5 meters per second in a very small raster pattern, right? So these galvanometers are shown here. This is just ScanLab. They make equipment for a variety of different research instruments, but they also make equipment for powder bed fusion systems. And it's basically a motor that's attached to a mirror. Nothing much more complicated than that, actually. When we get to systems integration controls part of this, we'll start to write equations of motion for this. But basically, this is how a motor works. You have a permanent magnet, you have an electromagnet, and you can drive this system around. This has then typically an encoder on it. For those of you who have ever done motion control in your research or seen this in a controls type class before, an encoder is a position measurement sensor. Right? And you can apply feedback loops to this to then control what is the angle of this mirror. And these are extremely precise, fairly expensive systems that go on here. And that would change it in one angle, and you would have two of these in this laser galvanometer to basically be able to have 2 degrees of freedom so you can position the laser spot in X and Y on the bed. Okay. Any questions about that? Okay. Radiative energy is spatially distributed. Okay, so we'll talk about some models for this in a second, but it's actually not all that trivial to figure out what the distribution of energy in a laser looks like, because a lot of sensors to measure this will just fry if you put a really high-powered laser in it. So people have to find other ways to do this. This is a fairly old paper in which they had a motor which they could spin at a very well-tuned speed, and then they had this polished rotating wire, and they had a laser here, and then they had some material that absorbs this laser. And so then when this rod runs into the laser path, it reflects off this off the rod, and it also then spreads it. So the energy that's usually concentrated, it spreads it, and that's down to the now threshold where they can look at this from a detector and not fry the detector anymore, okay, by basically spreading the energy. And so what you get is laser beam coming in. It's coming in and it's reflecting it. Basically, if it hits here, it reflects in this direction. If it hits here, it's going to reflect in this direction, etc. I wish I probably had that wrong, right? No, that's right. All right, and then it spreads it out. And so then they can have this detector and then have an oscilloscope attached to it and then look at the profile in time. And if you look at it, it looks like it's approximately Gaussian. Right. And so experiments like this motivate models for the laser intensity. Okay, so instead of direct delta, that's really the simplest function we can think of for a laser. We can look at something that's maybe a little bit more sophisticated, like saying or assuming it says a Gaussian profile. So those of you who haven't heard the word Gaussian, this is synonymous with a normal distribution for the energy, or a bell curve, right, is another way that people describe this. Okay, so what this is saying is that you have the highest laser intensity at the very center of that spot. It then is distributed in a Gaussian fashion. Keep in mind that a Gaussian fashion or a Gaussian function has a finite value at infinite distance from that center, right? So oftentimes in these models, they truncate this Gaussian once they get past a few sigma of this Gaussian, just to simplify their analysis. But this would be the Gaussian profile. This is something that we actually looked at quite a bit when we were looking at the introduction to PDEs. So this would be a 1D Gaussian or 2D, depending on how you specify this. But this would be the laser power. You have some sort of efficiency factor. I'll talk about that in a second. And then you have the radius or distance from the center, and then also the beam variance given by sigma squared. So this is your standard Gaussian distribution. And so what this is saying is that the power delivered by this laser is a function of the distance from the center of that spot of the laser. This is, if you look through the literature in additive manufacturing, you'll find a few, I don't know, maybe a handful, 5 or 6 different models. Everyone thinks they have the best model for a laser power distribution, but the vast majority of people who model this use this distribution as something that's fairly simple that captures the fundamental physics of laser energy impinging on a surface. Okay, so that's this is one step up in complexity from our Dirac delta function. Going one other step up in complexity, and there are ones that are even more complex, but I don't think it's really worthwhile addressing those, is a 3D Gaussian model. Okay. So the idea behind a 3D Gaussian model is that you have laser energy coming in, okay, in this direction, and then it's absorbed in a fairly random manner by powder. Okay, so you have this powder, and this is kind of a cross-section. This is just a bunch of powder that's kind of packed together, and so some laser energy actually gets fairly deep into the powder bed, right? Because it reflects on this powder particle, then this one, then this one, this one. Each time it's losing energy, but it's getting farther than just the top surface, the laser energy. Some laser energy is actually reflecting off, and it's going back into the chamber, right? And so you have an efficiency loss, given by this eta here, and also this profile is going somewhat deep into the powder bed. It's not just at the very top surface. So this is more of a 3D or volumetric model for how laser energy is absorbed into the powder bed. And then this would be your standard equation for a 3D Gaussian. And then the unique factor here is that you can start to specify the variance in the x, y, and z direction. So oftentimes, if the laser is focused appropriately, x and y variances will be exactly the same. So that means in the x and y direction that the power spreads the same in both of those directions. It doesn't create an ellipse in that direction. But in the z direction, it has a different variance. And that's because you get basically the power doesn't go very deep into the powder, but does go some distance into the powder before it's dissipated by all these internal reflections from hitting all these powder particles. Any questions about that? Okay, so that's basically how energy gets into the system. The next thing to consider is what happens when it is in the system. So this is fairly complex, so I'll go through this slowly. Please stop me if you have any questions on this. So we already know that heat is absorbed by the powder layer, right? So given that that's true from what I described in physical process 1, the question is then where does all this heat go, right? And it's going to have a lot of different pathways in which it's going to go. The first, I think, is worth mentioning is convection. Right? So we talked about convection. This is heat that's actually coupled with mass transport. Right? So you have some sort of fluid, and this fluid is moving across the surface, and with that, it's carrying heat with the convective source. So we have, I've alluded to this before, and we'll talk about this a little bit more carefully, and maybe today, maybe on Thursday, but we have a flow of argon gas across this top surface, and that's to basically to carry the spatter and any smoke that comes off the process away from the top belt surface. So you have forced convection going in this direction. You're going to have some, of course, some natural convection that happens from this. But basically you have losses from the top of this part into the chamber, or into the environment around this. The other one is that you have radiation. So that's either radiation because you don't have complete coupling of the laser. There's an inefficiency factor less than 1, light reflecting off that, or just simply the fact that this top surface of this part is hot and the build chamber is colder, right? So we know that we get radiative heat transfer when you have a temperature gradient, right? So we're going to have radiation into the build chamber as well. All right. Other things to consider is we're going to have, as was just asked, conduction into the powder bed, right? All right, so we have a hot part. It's assuming it's hotter than the powder beside it. We're going to have heat transferred into the powder. And so this is going to happen essentially everywhere, which is in contact with the powder. Right. And then the other thing that we're going to have is heat primarily through conduction passing through the part itself. And it's going to go from the part itself primarily in the negative Z direction to this build substrate. And we'll talk about models for how we model this build substrate. Maybe today, maybe Thursday, I'm not sure exactly how far we'll get, but this creates our heat sink. So this is what allows us to exhaust heat. So if this didn't exist, if we had some sort of thermal insulator for this build substrate, the part would get incredibly hot and you couldn't build anything anymore. It would basically just stay near molten for a long period of time, and you wouldn't be able to create anything. It's like this kind of massive molten metal. Right? So we have the primary heat transfer mechanism is going to be conduction through the part downward to the substrate. The substrate, just to remind you, we have to go back a few slides on this. You can see where it's been cut off here. That's the build plate. There we go. This build plate or build platform, build substrate, you see all of these terms used interchangeably, is just a really large piece of metal that you build things upon on top of. Okay, so really large. This is somewhere on the order of 16 inches by 16 inches, and somewhere about 3 inches thick. So, has anyone ever tried to pick up a piece of metal that heavy before, or that size before? It's doable, but it's you'll sweat a little bit. Okay, but we build these on really, really large pieces of metal, and that's if we want a heat sink. Heat sinks are more effective when they're really large in terms of trying to keep that part, this build platform relatively cool. Okay, so basically all the heat, most of the heat is going to be going into the build substrate as a gigantic heat sink. Yes?
So does your part or support structure actually fuse to that substrate?
Yes.
So you have to like cut it off and guess refurbish that, use that again?
Yep, you build it directly on top of the build substrate. Right. So oftentimes this example is showing the part built directly on the build substrate. Oftentimes, to make that removal process easier, you'll put support structures there because those are weaker, and those create a nice plane which you can cut. So I think probably maybe your next question is how do we cut these off? Usually a bandsaw, that's the cheap way to do it, or EDM, electrode discharge machining, would be the expensive but very precise way of doing this. Has anyone not seen EDM before? Okay, so electrode discharge machining, not electronic dance music, is it's a mechanism in which you put a high current through either a wire or some sort of part, and then you have the part itself grounded, and then you have this cutting fluid, not cutting fluid, but basically a certain type of fluid in between, and you're actually eating away that part surface. This is probably all scripted physics of it, but basically you're creating a charge between those two surfaces. You get a lot of current running through it that actually eats away the part surface in a very slow manner, but also very precise. So if you ever want to machine something and you have to have essentially no stress on the part while you're cutting it, you use EDM. And you want to have very high accuracy, use EDM as well. Other types of cutting processes have a considerable amount of stress you impart into the part. So, as you imagine, much more expensive than a bandsaw. So we build these directly on this build platform, precisely because we want really effective heat transport into that large heat sink, is the idea. I forgot to mention, so we have heat conduction through the part. It's also going through the support structure, and that's, as we discussed in the anatomy of a part, that's a primary function of that support structure, is actually to exhaust heat. So, like I said, if we have overhangs, like say anything less than 35, 45 degrees, that causes a big problem. So, of course, anything less than that, we're going to have support underneath it to allow the heat to dissipate from that region effectively. Okay, any questions on that? This is a pretty busy slide, but I think informative. Okay. Yes?
In powder bed fusion, is the support made of a different material, maybe to make it more conductive to have better heat transfer, break off easier?
People have toyed around with that idea. It's really tough to do because that means you have to, when you're spreading the powder, you have to spread the powder in a very precise manner in terms of this powder composition in this region and this powder composition that's for the part in this region. And so the recoder systems are actually pretty simple. It's like a blade that just runs across. And to do that would be fairly complex in terms of how you would handle that. Where you can see it, and we won't talk about that idea so much, but with the directed energy deposition methods, like the blown powder, you can pretty easily switch the powder streams that are being blown, and so you can change the material in a kind of spatially with the directed energy deposition methods. But with powder diffusion, it's kind of tough. I think the closest thing to what you're asking is that people have looked at chemical treatments that will, the chemical treatment will attack everything, but it'll if you have a very thin member, such as the interface between the part and the support, it'll eat everything equally, but a thin member will eat through quickly, where a thick member will take forever. So you can basically time how long you're etching that part, and then the support will fall off. But that's not current practice. There's just one professor at Arizona State that does that. And he's trying to get it to take off, but I don't know if it will. So. But it's a major problem. So in terms of how you move the support, it's actually, we have these really sophisticated tools that cost like $750,000, et cetera, even more. And then the support removal is basically some people with chisels and Dremels and stuff and removing it. It's very not sophisticated, the whole support removal process. Okay. All right, so this is more the macroscopic view of what's going on. The microscopic view, and I hope the video showed a little bit of this, of the high-speed video of what's going on in the melt pool a little bit, but you have, at the melt pool level, we have heat coming in from the laser. This is either absorbed, and it's also reflected, right? It reflects back into the environment above it. So this is going to cause heat conduction, or it's basically heats up this region, and then heat is going to transfer by radiation, because it's going to be now hotter than the surface surrounding it. Conduction through both the molten metal itself and anything that's not molten below it, a solid metal. We're going to have what's called Marangoni convection. This is something that we've alluded to thus far, but this is convection that is driven by a surface tension gradient, and that surface tension gradient is driven by a temperature gradient, right? So this is going to be the hottest area towards the edge where it's getting to the solid region. That's going to be colder, still very, very hot. But this is going to create a temperature gradient, which creates a surface tension gradient, which then causes a shear stress, and you're going to get flow in this melt pool. So those undulations that you saw in those video in the melt pool is primarily driven by this Marangoni convection. And then we're also going to have evaporation. So this is generally seen as unfavorable, but this definitely happens. So you are at least locally heating up this metal so hot that it's going from solid, liquid, then to gas, and actually evaporating in here. And so that is just like when you sweat, that's a heat loss mechanism, right? This is going to be a heat loss mechanism as well, but this is going to have some effect as well. So it's going to get evaporation. Any questions on that? Okay, so this is we'll see a video of this in a second. I wanted to show this. So Lawrence Livermore National Labs, they're doing a lot of really cool stuff on the science aspects of powder bed fusion. This is an extremely complex simulation of the process. And I think it helps slow things down, and you can start to see some of the things that are going on. So what you see here, the spatial domain on all these, I believe, is the same. Yeah, so the spatial domain on all these is the same. This is early time points. This we could say is equal to time, lowercase, is equal to zero, and this would be t final, down this right corner. Okay, so this is turning the laser on, right here, and then scanning across the surface. So this is the very instant that the laser turns on, scanning across the surface, and so you see it's moving from the rightward direction. Okay. So in these simulations, they're capturing a lot of what's going on. It's pretty amazing. You'll see a video of it in a second. But this is it turning on. You see then, the color corresponds to temperature. So reds are hotter, blues are colder, right? Okay. And then anything that is not really colored means it's solidified. Anything that has a color associated with it means it's in liquid state. Okay. So what you see here is you get this initial heating of the metal powder. You get also this hole driven into the material. We saw this with the X-rays as well. We saw basically this driving of a pore into this surface. In general, this pore gets more molten metal flown inside it, and so it collapses and doesn't cause a frozen pore to be permanently stuck in there. But you see there's this kind of divot or depression underneath the laser. So it goes along. You see in its wake, it leaves material that's getting colder but still molten, and then eventually, especially here, you can see it starting to freeze, right? This is the point where some of the material that was at one time molten now becomes solid again. You see, it's tough to see kind of the stills, but in the videos you saw particles being recruited into the melt pool. So basically you get some sort of migration and they flow into the melt pool. It leaves this area here that actually has a lack of powder, and they call that a denuded zone. So this is area that was fairly uniformly spread with powder. the melt pool draws the powder in, and now it has a vacancy of powder, actually. So it gets this denuded zone. You get a melt pool that is fairly smooth, but has some roughness to this. So this is on the order of just tens of microns. So if you were to feel this with your finger, you would feel a little bit of a ripple. It wouldn't be perfectly smooth like you can get from machining, but it's not too bad, right? It gets a fairly smooth surface. You get then here a pretty large depression, and then eventually this is then the laser turning off right here. This would be laser off. And then if you don't do this correctly, you can get this depression to remain. So that this pore could potentially be trapped. So just like you saw the X-ray video of the pore being trapped, this was a simulation in which they ran it at a laser power such that a pore was trapped. But they're trying to demonstrate what's going on here. But this is kind of in slowed down fashion. I would encourage you to, if you're ever interested in the more of the computational aspects of powder bed fusion, I'd recommend you at least look at all the pretty pictures in this paper. There are a lot. This is just one example of the process. They went through a lot of different conditions to look at how you get different effects with different powers, speeds, etc. But these are really, really complex simulations here. So here's the actual simulation from it. Let's see if this can run. Maybe. So the bottom video is the video we already saw earlier. All right, so this is, just to remind you, this is the experimental observation of what's going on. And then here is their simulation. And so this is actually the exact simulation that I showed in still frames, now in video, so you can watch this progress. So they have, this is pretty incredible, the type of simulation they're doing. You'll see spatter, you see that right there? They even simulate that, which is kind of crazy. In terms of like really detailed simulations of the process, Lawrence Livermore National Labs is really leading the way in terms of how to do this. Now, just to note, what you have here is a simulation that is really small. That's 1 millimeter by 300 microns by 50 microns, and this took 100,000 CPU hours to compute. So this is not like you can simulate an entire build using this, right? This is not a part. This is just a very, very small piece of material. So it's very computationally intensive to try and to do this, but it does give us some understanding of some of the things that are going on in terms of the physics that are engaged here. Any questions about this computational model here in terms of the things going on? Yes?
So is this only one powder layer on
Yes.
top of the substrate?
Yeah, exactly. So this is assuming that you have a piece of metal, and this would be like the very first layer that you're doing with randomly placed powder on it.
So what are the random hot spots, like on the edge of the metal pool, like way behind the laser? Like you can see like those red spots in the edge of the metal. Even in the laser, like right there.
Yeah, I don't know actually. I'd have to read the paper again and see if they comment on that or not. But you're right, they do kind of pop up somewhat randomly. In general, it gets cooler as you go towards the trail, but you're right, when the video restarts, you see something just kind of pop up every so often. I don't have a good answer for you. Yes?
Is that scale in meters per second? That's speed instead of temperature?
Oh yeah, you're right. Thank you. This one's actually not temperature. This is the speed of the fluid flow. Yeah. Thank you. Yeah. Thanks. So, still, even in regards to your question, I don't know exactly why you'd have high velocity regions at the tail. You see like the reds popping up at the very end of the tail right now, right? I don't have a good explanation. Okay. So with that, I think this may be a good time to take like a 5-minute break, and then we'll get back into it.
simulations will run on CPU time as opposed to GPU?
They reported it as CPU time, yeah. I mean, it was still a supercomputer.
Right,
Yeah, they were occupying one computer for years, right?
Right.
Yeah, still on supercomputers. This is total number of CPU hours if you add up all the processors going. And this is basically if you decide to you want to include all physics that we know of where that's relevant into one simulation, this is what you get. So.
We actually have like real powder bed. Those are the actual particles, the spheres.
Reasonably close. Were you at the presentation on Thursday where, where the presentation was basically showing that certain levels of quality have different, or more, basically certain powders are more spherical depending on how much you're spending on it. So I was going back to, so it was given on Thursday, but also I addressed it with less rigor when we went through just some examples of, there we go. So here be SEM images of some common powders that would be used. So you can see that they're roughly spherical. You can see ones that are definitely not spherical. So those pop up randomly. You can imagine it's impossible to really, in an efficient manner, tease these out and pull them out, right? So you get a pretty random variation, and that's also the size distribution is they're not all one size, right? So their simulation, you can see in the simulation they use uniform powder size, right? But that's definitely not the case. You get a distribution of powder sizes. So this is laser PBF powders, this is E-beam powders. So fairly spherical, but definitely not perfect spheres.
These new videos and the particles are refused to the general stream. Like sphere roughly connected to the overall part they're making.
So like these.
Yeah. Are those dealt with in post-processing? Are those sort of just sanded off
The-
and part is sort of ready to go?
Depends what you need. So the part I passed around, you can actually feel it's rough, right? It's not like you get off a CNC mill, right? A CNC mill oftentimes is a very smooth finish. So it depends from an engineering point of view what you need. Right? So if you need a very smooth surface, then you probably have to do some sort of finish machining on it. If it's not a requirement, then that's probably an unnecessary expense to go through and then make it smooth.
Curious, do you think like PBF will like go the way of FDM printers when the patent expires just because of all the support structure?
Go the way in terms of become less expensive,
Yeah,
you mean?
people like having like their desktop 3D printers.
There's a lot more going on here in terms of things that spike the price.
Yeah.
There's in FDM. There's basically 4 motors, and there's a heating element, and then some computer control. And this has a lot. Anytime you have a system that has regulated air quality, including vacuum pumps, argon sources, things of that nature, then it gets much more expensive. So, but there is. I mean, you asked the question. I think it's important to know too. When I went through that table of different suppliers of powder bed fusion systems, there's a company called Formlabs that's doing polymer powder bed
it's
fusion.
LA.
Yeah, well, they have a powder bed fusion system now too,
Oh, yeah.
and it costs around $10,000 or so. But with the polymers, you can do that in atmosphere. You don't have to do it in a vacuum or argon environment. So you don't have to have a really robust chamber, and so that makes it a lot cheaper. Lasers actually, especially low power lasers for polymer melting, those are pretty cheap actually. The higher power ones are expensive. And then also the powders are really expensive too. So metal powders, I think somewhere around $20K to fill up a chamber full of like titanium powder, maybe more. So it's not a cheap endeavor. You have to really want to make something that you're going to sell for a lot of money to do it. Okay. Okay. So this is just a little bit of a repeat of this is a repeat of that table I showed earlier on in 5 to give you a sense of different temperature profiles here. The main thing to point out is we have ways in which you can measure with reasonable accuracy the temperature of the melt pool, and so this is an example of temperature of one of these melt pools. The temperature of this melt pool peaks at a variety of different levels. This is from a single paper. I think you should take this with a grain of salt. It's really highly dependent on the material that you're talking about, and also how you're operating the system. This is, I've seen all the way up to 500 or 5,000 Kelvin for some examples where they actually either predict or measure the temperature at the the peak temperature in the melt pool. But this gives you a kind of a sense of the temperatures experienced. So this is, if you have this image, right, this is a two-dimensional heat map, but you can also basically plot these along the distance. This would be the very peak temperature in the melt pool, and then you can look at this temperature here. So you see a few things that are important. So this is, in this case, around 2,400 degrees Kelvin. I'm sorry, 2,400 degrees Celsius, so I add 273 to that to get Kelvin, right? And then you see a few things. You get a really steep temperature gradient here, and then in front. In front doesn't really matter all that much because that's about to be melted anyhow. The temperature gradients as we get into the solidification mechanics in a later module, we'll talk about that, but this temperature gradient actually makes a big difference in terms of how the crystal structure of the metal is formed. Okay, so you see a really sharp temperature gradient here. This is along this direction, the melt pool, but you also would expect that there's going to be a large temperature gradient in this direction as well. And then you see shallower temperature gradients in the tail. So these are just observations or what's kind of known, and these are people have measured before in terms of trying to understand this. Okay. All right. So with all this being said, these are in kind of a very quick manner some of the physics that people consider when they look at powder bed fusion. And then it's worth looking at some non-dimensional numbers to try and figure out if we can try and simplify our analysis a little bit. And so what I'm going to be doing here is going through these non-dimensional numbers so we can try to understand, all right, what's important, what's really important, what's somewhat important, what's not important in terms of trying to model here, so we can try and make our analysis more easy. And then once I go through and say, all right, here's what's really important, somewhat important, not important, we're going to strip away everything except for the very, very important aspects and do some simple analyses there and then start to build some of that complexity back in. It's kind of the methodology we're going to work with here. Okay. So let's see what we can simplify first. All right. So first off, and this is getting to the question I was earlier in class, is conduction, convection, radiation into neighboring powder appreciable? Is kind of the question that was asked. Does it matter? Do we consider, if this is our part being built in the raster pattern, so this is everything that's been solidified, everything adjacent to that is unfused powder, do we care, or are we going to model this heat flux into the neighboring powder, is the question. And so what we're getting to here is really a multimedia heat conduction problem. And so this is kind of like when you get into heat transfer class from undergrad, this is something you did probably within the first 4 weeks or something. And when you look at, all right, what's the effective conductivity of this material and effective conductivity of this material in terms of trying to understand temperature gradients and therefore heat loss through this part. And the main thing to mention here is that if one of these conductivities is really, really low, then we consider that to be a Newman boundary condition, right? We can effectively say that that material has very poor or very inefficient heat transfer through it, so therefore the conduction is going to be very low in terms of heat flux. Okay, so people have reported on this, and so some things to look at here. If we look at, this is a fairly recent, this is getting a little bit older, but people have looked at what is the thermal conductivity of stainless steel, iron, copper. Stainless steel and regular steel, or essentially iron, is used in powder bed fusion. Copper, never. But this was a study they did on powdered metals. But so you have these types of thermal conductivities. So just kind of give you a range, stainless steel on the order of 15. Okay. And then they did some experiments. They did a lot of thermal analysis with the experiments, but then they looked at stainless steel, 316L, at different packing densities. They basically took all these particles and they packed them at different densities here. This is about in the range that you see in powder bed fusion, and you get thermal conductivities at around 0.15, right? So it's about 2 orders of magnitude difference. Is that legible, or is it tough to see? Very tough to see, but it's legible? Okay. All right, so around 0.15, so 2 orders of magnitude smaller in terms of the effective thermal conductivity of powdered metal versus solid metal, or bulk. Same thing with iron. You see 74 here, and the iron you get somewhere around the same level. And then with copper, copper has extremely high thermal conductivity, and yet you see the effective conductivity of copper powder is right around the same level of stainless steel powder. And so the main message of this work is that it's actually not the material properties of the powdered material at all. It's actually the air that dominates the thermal conductivity in a compact of powder. Okay, so regardless of what material you're using, really everything is dominated by the air in between in terms of thermal conductivity. And then the other thing is that if we do a ratio of the thermal conductivity of the powder to the thermal conductivity of the bulk, it's less than 0.1 or 0.01. And so the main message is that we can pretty safely neglect thermal conductivity into the surrounding powder. Right? It's less than 1% of the equation, essentially. Okay. So I'm not saying like I'm saying this is essentially become the standard in the field of trying to model the physics of additive manufacturing. It's one of the first things people do is they say, all right, let's simplify the problem. And what they do is they say that this is a Newman boundary condition at the edge of the part. Okay, so here's the schematic. This is some part, and then this is partially through the build. Okay, so we have basically simple rectangular part. This is the raster path, and then this is where the raster path will be in the future, and then you have regions. I'm not showing all the unfused powder here, but that was to be on this side, etc. But we then impose if this is domain is D, anything that's kind of like this light gray, the Newman boundary condition is placed at the edges here, in between the unfused laser or unfused powder and the top of the previous layer. This top layer, all of this would be the Newman boundary condition. Here. Any questions on kind of the motivation for that? Okay. But this is one of the most standard assumptions you'll see. Okay. All right. Then the next thing to consider is convection and or radiation into the billet chamber appreciable, right? So we already talked about into the powder around it. Now we're looking at this top surface here. Do we care about heat being lost to the atmosphere, either by convection or radiation? Okay, so first the convection problem. We did an example of this with air, just to make it as a simple material or simple fluid that everyone's very familiar with air, right? Air is great. But these chambers are usually argon or nitrogen is the surrounding the fluid around it. And then I mentioned before is that in these processes you have gas flowing across this top surface. So here's your part being built, here's your melt pool, laser, you have a cross stream of gas going from the inlet to the outlet, and this is to exhaust the smoke that is formed. Right? So we're trying to remove the smoke from the top of the surface and causing problems with basically weakening the laser as best possible, get rid of any soot that forms, spatter, etc. We're trying to get rid of that. And so what we have is forced convection across this top surface. This is your pretty standard forced convection problem over a flat plate. So here you have this velocity profile. So you have a free stream velocity, and then you're looking at, all right, is there appreciable loss of heat via convection at this top surface here? Is that something we want to consider when we're considering boundary conditions of our domain? Okay. So the gas is primarily argon. Very common, it's 1 atmosphere, so it's not under vacuum, it's not under pressure, just kind of normal atmospheric pressure, and it's primarily argon. They do their best to get oxygen out of it and anything else that's normally in the air, but you can't completely do this, but it's less than 0.1% oxygen usually is a kind of the threshold they shoot for. And then if you look at the literature, you can see some estimations or measurements. In this case, this is actually a measurement of the free stream velocity using a hot wire anemometer. And it was ever done in fluid mechanics studies or a background in aerospace engineering. They've probably seen these before. But there's a free stream velocity of this airstream of about 1.5 meters per second. Okay, so quite fast actually. And then the way in which we analyze this is using the Biot number. So I've read a lot of literature on this because we did a lot of modeling of this process, trying to figure out where people come up with the Biot number for the process, and people say it's less than 0.01. I've never seen anyone actually do it themselves and prove it to me. So here's us proving it. That's going to be very, very small in terms of the Biot number. So here's example 5.1. Consider a rectangular block of 316 stainless steel. We could, of course, put in our favorite material that we want. This is a really common material to build from with powder bed fusion. So it considers a rectangular block. Thickness of 0.05 meters. Oops. Length of 0.1 meters. Base temperature of 373 Kelvin. So this is 100 degrees Celsius, right? So this is a pretty common operating environmental temperature for powder bed fusion. And then we're saying that the surface on average is 100 or 1,000 K. So we're not looking at directly at the melt pool, which in terms of the amount of space that takes up, that's actually really small. We're looking at the surface and what is about the temperature of this surface. And then we have argon gas at 1 atmosphere. Temperature of the environment, again, 373 K, and it's flowing across the surface at 1.5 meters per second. So this is quite similar to example 4.2. from the non-dimensional methods portion of this. Okay, so if you want to look back at that, went through a little bit more detail on that one, but the properties still hold. If we have 316L stainless steel, the conductivity of that material, 19.1 watts meters inverse, Kelvin inverse, and this is in that survey paper. Okay. So this gives us part of the Biot number, right? So the Biot number is convective heat coefficient, or convective coefficient parameter L. This is the thickness of the block, and then K is the conductivity of the solid material. Right, so this gives us part of the equation. The next is the tough thing to find is finding H. All right, in this case, it's actually H effective. So this is the H effective. And it's H effective because the convection coefficient is different at this leading edge as it is from here. Okay, so we often look at H effective or average H. And so to start this, though, we need the Reynolds number. So we need to understand, is the fluid flow laminar or is it turbulent or transitional? So as a reminder from previous lectures, Reynolds number for flow over plate, density, free stream velocity, the length of the plate over then the viscosity. And then we can pull some of these values for argon gas. This was actually from just engineering toolbox, is where I found these, but the density of argon gas. All right, about 1.5 kilograms per meters cubed. Viscosity. Prandtl number, we'll get to this in a second, but this is the material property. And then last one, we need to know the conductivity. This will be for the next equation, conductivity of argon gas. Yes?
Because the argon is gas, can we find density through like a state equation, like ideal gas law?
Yeah, so this is looking at a table, and they had this is just a lookup table actually I used. So the density changes with well, basically pressure and temperature, right? So this is at the temperatures that we're considering. Yeah. Okay. All right. So Reynolds number of this flow, you can plug all these in, but you'll get a Reynolds number of So this is Reynolds number at the back edge of this plate of 1.21 times 10 to the 4. So oftentimes we consider the transition between laminar to turbulent to be around 10 to the 5th is where we consider that for a flow over a flat plate. Right? So the main message here is that we have laminar flow. Okay. So if we would have gotten turbulent flow, I would say the engineers are designing this incorrectly. It would probably not make much sense if you had a bunch of turbulence in your flow over this stream that's not supposed to affect the laser very much. Okay. So laminar flow, we then have to get the effective heat convective, or the average heat convective heat transfer coefficient. So from example 2.4, or sorry, 4.2 from previous classes, we have that the average convective heat transfer coefficient is equal to the average Nusselt number over the conductivity of that gas over the length considered. And then other numbers, Nusselt number. Okay, so this gives us a Nusselt number. We have everything we need. We have the Reynolds number, we have the Prandtl number. Nusselt number is 63.9. And then we have the effective or average convective heat transfer coefficient, plugging everything in here. Approximately 11.0 watts meters -2, K -1. And then we throw this all into the Biot number. Okay, it gives us 0.029. So again, the Biot number is the ratio of convective heat transfer to conductive heat transfer at a surface, right? Right. So we're saying that the convective heat transfer is about 3% of the conductive heat transfer at this point. Okay. Oftentimes the cutoff before whether or not you consider convective heat transfer is 0.1. This has just been established in the heat transfer community is kind of a cutoff on where you consider this or not. So we're satisfying that by about a factor of 4. And so the main message, and this has been, this is the main argument for a lot of work in powder bed fusion is they ignore convective heat transport. And on Thursday we'll go through the nuance of where we do and do not consider convective heat transport. In terms of convective heat transport into the surrounding fluid, the air or argon gas in the chamber, oftentimes we neglect that. Some papers will include it, but the majority of the time this is not included. And so the main message here is convective heat transport into the chamber is not appreciable. Okay, it doesn't satisfy this cutoff for the Biot number. Convective heat transport in the melt pool is going to be very, very high. And we'll talk about that later, but from the surface up into the gas above it, very low. And so, oops, I'm skipping a slide I wanted to have in here. I was intending to put the slide in and I forgot. So going back to this one, what that's going to do in terms of this, I'll add this slide back in. What it's going to do is it's going to create another Newman boundary condition here as well, right? So all these sides here covered in powder, this top not covered in powder, this is open to the gas above it, right? With a flow of air across the top, and we're going to say this is a Newman boundary condition as well in this region. Okay. Any questions on that? All right. So just to kind of recap, we'll talk about this boundary condition, the build plate, on Thursday. Also, we have a presentation from AJ, right? You seen? No?
Yeah, I know.
Brian?
Yeah, this is me.
Okay, you had a panic look in your face, so
Yeah.
sorry to do that to you. I do that every week to some random student. So. Brian, okay, all right, never mind. All right, so we'll have, on Thursday's class, we'll have Ryan present either the beginning or end, whatever you prefer, and then we'll go into more of these details. So we've kind of started to build up what's surrounding this domain, right? We have mostly Newman boundary condition everywhere here, except for this build plate. We'll talk about what that looks like on Thursday. All right, see you on Thursday. Sorry?
So, the example you just gave, for
Yeah.
it should be perfectly flat, right? So we're not.
It's a simple.
Okay. So we're just assuming that the powder is smooth enough that we're not, there's not enough flowers.
That'd be an assumption. If the end number is getting a little bit closer to a 0.1, then maybe we would have to be a little more careful with that, but we were pretty far away. Well, in fact, we're 4 away from that, so.
Is there any research into maybe like eliminating the need for like a heated enclosure for argon? Is that absolutely necessary for?
We definitely don't have oxygen in there. So, not that I'm aware of. That's like the most standard environmental control.
Is that like the biggest cost for the additive manufacturing of metal?
Well, probably not. I think everything's expensive in these types of machines. So, I don't know what the biggest cost is, but anytime you have enclosed chambers, it balloons your costs. So, and pumps and all that other stuff that goes along with it. So, but yeah, like everyone uses some sort of inert gas.
Okay.
Because metal oxidizes very fast.
Thanks. So for the presentation Thursday, you want like a copy of that emailed over or something beforehand, or how do we want me to get it to here?
So last time we just had a thumb drive,
Okay.
and then we recorded it too, so it will go on the YouTube channel. So that's how people can access it.
Okay. I don't know that I have direct access to a thumb drive right now, but I can figure something out.
You need to sign up for some sort of promotion, you'll get one free.
Yeah, I'll figure it out. Okay. And then I think I got the general idea, but just make sure, kind of like just general overview of what the article's talking about. Just kind of talk through some interesting points.
Yeah.
With the overall summary.
Yeah, and you just keep in mind, like this is mostly, it's more for you as the presenter than it is the students themselves. So it just gives you an opportunity to kind of dive deeply into a certain work,
Okay.
try to understand it. If there are things you don't understand, that's perfectly fine too as well. But maybe pick a few aspects you thought were really interesting that you do understand well and you can explain well. And if there's something you don't understand, you can always talk about like, here's what I think's going on, but there's some things that I wasn't 100% sure on. But basically, it's your best attempt to try to understand. It's a pretty complex paper you picked. So.
Yeah, it's pretty dense.
Yeah.
I've read it a couple times, but I'll probably read it again.
Yeah.
Okay. All right, well, that makes sense. Should be a problem. Thank you.
Yeah.